All right, so hello everyone. We are very happy to have a PhD defense of Amir Behrouzi-Far today, and I would like to thank his committee members for being here, and in particular, Professor Gauri Josie from CMU. She's our outside member, and we are really happy that she took time to take a look. This is similar in the line of her research, some of her research, and also actually similar to this particular chapter that Amir will be presenting, may remind Gauri to her Bell Labs internship on overlapping generations. So anyway, without further ado, Amir, the floor is yours.
Thank you. So welcome to my PhD defense. So yeah, let's start. So the title of my PhD thesis is Redundancy Scheduling for Fast, Predictable, and Timely Response in Distributed Systems. It consists of several chapters. So I worked on multiple problems in my PhD. The first problem I worked on was redundancy scheduling in distributed computing. I published a paper in Allerton 2018 and then extended that to a journal paper in transactions on networking. And then I worked on like the problem today I'm going to talk about, which is non-adaptive redundancy scheduling. I talked about this problem in Allerton 2019, and then we just submitted the journal version of that in Journal of Selected Areas in Information Theory. The third problem, which I worked together with Professor Yates and Professor Shoryanin, is timeliness in replicated storage. We had a conference ISIT paper, and the journal version is in preparation now. I also worked with my colleagues in the lab on a problem about load balancing in distributed storage. We published that in a conference, and also IT transactions on information theory. We published a journal version of that. And I also have worked on a reinforcement learning problem about timely asynchronous Q learning, which I will also talk a little bit today about. So today's talk is, so let me tell you about my other works. I had poster papers in IEEE Big Data 2019. I collaborated with Rutgers Mathematics Department about a problem that actually today I'm going to talk about again. We have an archive paper with Professor Zilberger in Rutgers Math Department. I also did a summer internship at Warner Music Group, and I did some work on graph embedding and several other machine learning problems. So today's talk is about balanced non-adaptive redundancy scheduling. So these problems I talked to you about, I talked about one of them in my qualifying exam, another one in proposal, and I touched on this problem in my proposal, but I didn't have enough time to explain what's going on. So today I'm going to give a full talk about it, and yeah, hopefully everyone will have a good idea about what it is. All right. So what is non-adaptive scheduling? So non-adaptive scheduling is about is when we want when we have different servers and we want to schedule arriving jobs to those servers. If we don't have the side information about the actual workload of the servers at the time of scheduling, that's called the non-adaptive scheduling. And it's actually, and there is the other counterpart, which is adaptive scheduling, where you have this side information and you are going to send the job like to the least loaded server every time. So this adaptive scheduling is not something that you can easily use in practical scenarios. Well, because first of all, the service requirement of jobs is hard to estimate. Like over provisioning of resources and under provisioning of resources is a very usual problem. in practical systems. And besides that, the overhead of estimating the workloads for each job, for each arriving job, the overhead of estimating the workload on all the servers is prohibitive in larger scale systems. So then, yeah, we want to do non-adaptive scheduling in practical systems, but then we don't have this side information about workloads. And so we are not able to distinguish the less loaded servers. And we might end up sending a job to a server which is already overloaded. So that's not good. So we have to think about that. We want to have a blind decision, but not but we want to make a good decision as good possible. And also in a real system, there is randomness, and randomness can be like from server side because they have unpredictable slowdowns, or it can be actually because of failure to accurately predict the service requirements of the job. So that's another source of randomness in computing systems. And this randomness is not desirable because, well, it can increase the expected waiting time in the system, which makes the scheduling problem more harder, because then we are dealing with something that we don't exactly know how much is it gonna take, and so on. So, all right, so the bottom line is we want to, at this scheduling time, we want to find the less loaded servers, but with non-adaptive scheduling, we actually don't know what it is, right? So then, okay, we can use redundancy. We can submit a job to multiple servers and hope that one of those servers is less loaded, and yeah, the job can end up being serviced sooner. But redundancy is not a solution in and of itself. And the reason for that can be seen in this system at the right side. So let's say we have two kinds of jobs. Like we have large jobs like elephants, and we have a small jobs like mice, right? So here, the green mice, which is a small job, there is a redundancy for that, and there are two copies of that, but both copies are behind elephants, right? So despite having redundancy, there is no diversity in waiting time for the green mice, right? So we have a redundancy, but redundancy does not help that much. And actually having this like kind of bimodal service requirement of job is something that is observed in practice. And this figure is from Google cluster traces. Like the average task duration is either very small or it's very large. So then in these situations, having like using redundancy blindly might not gonna help. All right. So then we move one step forward and we say that what we care is diversity, not actually redundancy alone. So at the right system, we have redundancy without diversity. And on the left, we have redundancy with diversity. Now the green mice is behind the elephant in server 1, but it's behind another mice in server 4. So hopefully in server 4, it will end up to service much faster. All right. So redundancy in literature, redundancy has a great literature in distributed systems, like different forms of redundancy, coded redundancy in storage systems have been studied by Professor Joshi, and coded distributed computing by our, yes.
Do you mind elaborating what do you mean by redundancy in the previous picture?
Redundancy, yes.
Oh,
so
I meant diversity. So that's what I meant. So.
Oh, diversity. So diversity is diversity in the queuing, in the time that a job spends in queue. So
Diversity over time slots. Okay.
yes, yeah,
Okay.
diversity.
Okay, thank you.
In a way, but these two green mice have the same picture in front of them.
Yes.
So there is no distinction in that sense, although there might be diversity because the time is random just because of replication, but
Yes. Yes. So, and my lab mates have, and myself has studied distributed redundancy in distributed computing. We analyze latency, and also in queues, power of descheduling. The performance of power of descheduling was derived by Gardner et al. At 2017, and there are a branch of other works working using combinatorial designs for a smarter way of scheduling redundancy. And actually today I'm going to talk about using combinatorial designs later. So what we are after here. So what we want to do is we want to be able to compare the performance of different scheduling policies in system with redundancy. So that a more like a straightforward, the more direct, a direct way of comparing the performance of different scheduling policies is to find the closed form of whatever the performance metric it is. Like for instance, the waiting time in the queue. Like if one can find the closed form for that, is the best way to compare the performance. But this is what like finding, analyzing, and driving the closed form is a very hard problem. And there is not much, there has not been much progress in the literature about that. So we want to provide some performance indicators with which we can actually compare these scheduling policies with systems with redundancy. And how do we approach the problem is by making an analogy to the classical Urns and Bowles problem. And then we introduce some performance indicators in that analogous problem, which we argue that we can use them as a performance indicator. And actually later in the simulation, we show that they are actually a good indicator. And then we also propose a new scheduling policy based on combinatorial block designs that improves these performance indicators and have a better performance in actual queuing system.
Amir,
Yes.
I noticed your slide said that your policies are not adaptive. They don't schedule in response to what jobs are at the servers, right?
Yeah.
But when you schedule, do you know if the object you're scheduling is a mouse or an elephant?
No.
So that only the server finds out if it's a mouse or an elephant, and you don't know what you've assigned to which server.
Exactly. That's
okay. All right. Thank you.
So this actually there is this work of Gardner, which derives the average waiting time in redundancy D problem, where the scheduling policy is random and service times are exponential. But here we are going beyond random scheduling and also beyond exponential service distribution. And we want to be able to compare different scheduling policies. So here is our analogy to the Urns and Bowles problem. So let's say we have this queuing system where only arrivals happen. There is no departure. So there is no queue, there is no service, there's no server, there is no service. And because we don't have departure, like each queue will be an urn and jobs will be balls. So now we have urns and balls instead of a queuing system, right? And so in this Urns and Bowles analogous system, we want to measure two things. We want to measure load balancing by measuring the number of balls in each urn after performing certain scheduling. And then we also want to measure diversity. Diversity is like, it's going to be measured by some kind of overlap between the subsequent overlaps of urns between subsequent balls, which I'll elaborate later. So now, yeah, so diversity, we said diversity is important, and we are going to measure that here. So, but first, we're going to measure load balancing. So the load balancing factor is so here's this. So we have this urns on balls setting. We throw T balls into urns, and each ball is going to be placed at the different urns. So this is what de-redundantly means. So T balls into N urns de-redundantly. And we define our load balancing factor as the ratio of the number of balls in the minimum loaded bin and the number of balls in the maximum loaded bins in the limit when T goes to infinity. This is so this is not the only way to define load balancing. Yeah, it's not the only way, and we can do some other things, but this is the way we defined load balancing here. Yeah, there are other, like we can do like expected value of maximum over the average or something else, but yeah, this is what we are doing here.
Amir, I have a quick question.
Yes.
So this load balancing factor definition won't take into account whether you have the same, you have replicas of the same job blocking you in front, right? So if there are two elephants in front of two mice versus one elephant and one mouse in front of two mice, this won't consider that.
No, this is just load balancing. The diversity, like the performance indicators that measure diversity are going to take care of that.
Okay, I see. So you are going to define a different metric for that.
Yeah. So this is exactly, this is only the number. There is no mice, there is no elephant here. It's just a number. But later we are going to take care of that problem.
So to follow up on Gauri's question, Amir, in some other sort of notation, if you knew the sizes of the jobs, you could weight these by the sizes of the jobs, but you don't. You just count them, right?
Yes.
Okay, thank you.
Yeah. All right. So now diversity. How to measure diversity? So we measure diversity by the number of overlapping urns between randomly chosen pair of balls. So we are, after throwing too many balls into these urns according to certain scheduling policy, then we can define a set P of all the pairs, like T choose two pairs of these distinct balls, and then let's define X as one randomly chosen element from P. So X could be, like, for instance, in this example, X could be 1 and 2, 1 and 3, or 2 or 3. And then we define a random variable OX, which O sub X, which is the number of overlapping urns between the pair of balls in X. Okay, so in this example, we have 3 balls thrown into 4 urns, and so our P has 3 elements. If X is equal to if X is pair 1 and 2, then OX is going to be 2, because ball number 1 and ball number 2 overlap in 2 urns, urn number 1 and urn number 2. If we look at ball 1 and ball 3, OX again is going to be 2, because ball 1 and ball 3 again overlap at in 2 urns, urn 1 and urn 2. And for ball 2 and ball 3, the OX is equal to 3, because they overlap in 3 urns.
But this doesn't account for the order, right? Either.
No, it doesn't account for order.
Okay, because my impression was when you were talking about the mice that the order mattered.
Again, we are going to talk about that. Here, order doesn't matter.
Okay, thank you.
Yeah. So based on this overlap based on this random variable O sub X, we are going to define two more performance indicators. The first one is average overlap factor, which is the reciprocal of the first moment of OX as t goes to infinity. And so basically, if possible, we would like a scheduling policy to provide less overlaps on average. And so the greater the average overlap factor, the better a scheduling policy would be. And the more important performance indicators is overlap diversity factor, which is the reciprocal of the second moment of OX as t goes to infinity. So not only we want to have on average small overlaps, but we also want these overlaps not to be spread too much. We don't want to have small overlaps in some place and large overlap at some other place, right? So this is exactly what we don't want, because if you remember here, like on the figure on the right side, there's like these mice, the green mice overlaps in 2 places with the elephant and in 0 place with the other mice. So this is something we don't want. This is against diversity. We want to have uniform overlaps as possible. So that's why
Amir,
yes,
this OX is a random process, right? That somehow
is a random variable.
Well, it's a random variable at any particular time instance, right? But somehow, like as t goes to infinity, are these capital T, are these bins getting more and more filled, and this OX is for any X monotonically increasing, or I don't understand what it means to consider large T, and I'm not sure how OX changes over time.
Yeah, so OX does not change over time in the sense that we throw all the balls into the system, right? And after throwing the balls, too many balls, we are going to measure, so after throwing too many balls into the system, then we are going to study this system. Then OX is going to be a random variable. So we are not considering any time here.
So this limit as t goes to infinity is kind of a detritus, like it's like in what, like it's you're really talking about the instance after you throw all the balls into all of the bins.
Yes.
Okay.
Capital T, I think,
Yeah.
balls, right?
Yeah, capital T is balls. Yeah.
Oh, capital T is balls.
Yes.
Yes.
Uh-huh. Okay, but so the number of balls is going to infinity?
Yes.
And do they all have like different labels, or like, okay,
No.
so how come?
There is no label again.
Well,
So how we so here is how we control overlap. So what we care about is overlaps. We don't care like whether it's a small job or large job. So we are saying that if we can control overlap, then we can control diversity, and that's what we are after. And
OX is X is you pick a pair like server 1 and server 2, right?
Yes.
And then OX is when you're all done throwing the balls, it's the number of balls that were thrown into both bin 1 and bin 2.
No.
Is that right?
OX is so X is a pair of ball. So when X is known, then OX is known also. So X is a pair of ball, and OX is the number of urns that those 2 balls share.
Ah, okay. Okay. All right.
Okay.
So in this OX then is just defined for how those 2 balls, the balls in X, are thrown, and it doesn't depend on all the other balls.
No. Yeah.
Okay. All right. I think I understand those. Thank
All right.
you.
It's a heuristic. Yeah, I mean.
Yes. So yeah, so which scheduling policies we are going to consider is the random policy, where each job is going to get scheduled to these servers uniformly at random, picked uniformly at random. And then we have round robin policy, where the servers are picked in a round robin fashion. And we are going to propose a block design based, where servers are going to be picked according to the blocks in a combinatorial block design, which I'm going to talk about in a little bit. All right, block design. So first, let me tell you some introduction about block design. So a block design is a pair of chi and A, where chi is a set of objects and A is a set of non-empty subsets of X, called blocks. So it's defined by two sets of objects and sets of non-empty subsets of objects. So one of famous block designs is balanced and incomplete block designs, where is defined as by three parameters. Nu, k, lambda. Nu is the number of objects, k is the number of objects in each block, and every pair of distinct object is containing exactly lambda blocks. And a famous example of that is phonoplane, where it's a 731 design, where there are 7 objects, each there are 7 lines in 6 straight lines and 1 circle in this plot. Each line contains 3 objects, and each pair of 2 objects are only in 1 line. They occur together only on 1 line. So BIBD basically is a tool to diversify redundancy. We use it as a tool to diversify redundancy. How does BIBD do that? It's basically by sending each distinct pair of jobs to exactly lambda servers. So in case of a 731, each pair of jobs is going to be sent, each pair of jobs are going to be scheduled into 1 server only. So if you have 731 scheduling, then the first job is going to server 1, 2, and 3 in the first block. The line that mentions 731 BIBD is a set, and each set is going to be and the set is going to contain 7 blocks. So the first block is server 1, server 2, server 3. Means that job 1 is going to be assigned to server 1, server 2, server 3, and the second job is going to be assigned to server 1, 4, 5, and then the third 1, 6, 7, and this continues all the way to the job 7. And so this BIBD scheduling is diversifying redundancy. Like if you look into these jobs, like for instance, job number 4, job number 4 is behind job 1 and job 2, which are relatively large jobs here, but it's also behind job 3, which is a smaller job. So that's why it makes sure that 2 jobs only co-occur at one server, not more than that. And that's how it provides diversity. So is there any question on up to here? All right. Oh, I have to play all this. So then we are going to derive performance indicators for
Amir, one quick question. In the previous slide, for the BIBD scheme, there are 3 parameters, N, D, and 1. What is the third parameter? What does it represent? I didn't get that.
The one is actually lambda. It's the number of servers that 2 jobs co-occur.
So maybe if you show the funnel plane again.
Yeah. So like each pairs of job co-occur only in one line in this funnel.
Oh, I see, I see. So the overlap is 1. Got it.
Yes, overlaps. Okay, now we want to drive performance indicators for random policy. So now we have defined 3 performance indicators. One is load balancing factor, average overlap factor, and the other overlap diversity factor. And we are going to drive all 3 for our scheduling policies. So with random, in order to drive the load balancing factor, which is the ratio of the average number of balls in the minimum loaded beam to the average number of balls in the maximum loaded beam. So for this problem, I struggled a bit to drive this, and then I went to this Rutgers math department. I talked about this problem with Dr. Zilberger, and he also said that well, he did help me to have some idea about it, but he published this problem in his own personal journal, and then like a few days after, there was this PhD students from UPenn that he derived this our load balancing factor, which he basically used multivariate central limit theorem to drive this average number of balls in the minimum and maximum loaded beam. But for AOF and ODF, because they are defined based on the moments of random variable OX, we need to find the PMF of random variable OX, which is again straightforward. So the probability of OX being equal to a certain number, K, is D choose K n minus D choose D minus K over n choose D. And so based on that, we are going to find the first 2 moments of OX, and the performance indicators are derived. For round robin policy, well, we know that round robin is a perfect load balancer in the sense that it's going to send equal number of jobs to each server because it's round robin, and the load balancing factor is going to be equal to 1. We have AOF. Again, for AOF and ODF, we are going to find the PMF of OX. Again, it's when all the jobs are sent according to a policy. When we know that, like, how that policy is going to put things together, deriving this PMF is straightforward, and according to that, we can derive the first 2 moments again, and then performance indicators. And
Amir, do you mind going a step back, just a slide back? Okay, so here your LBF depends on T, but AF and ODF don't. Is that because they're in the limit and LBF is not in the limit?
LBF is also in the limit. That's a good question. But LBF is also in the limit, but yeah, I have to yeah, I have to double check this.
Okay, thank you.
Yeah. All right, so this was round robin, and then we have BIBD based policy, where again, everything is the same. The procedure is the same for finding the performance indicators. And then here are the performance indicators all in a table. Well, I don't care about most of it. The only thing I want to have your attention about is average overlap factor, which is the same for all three policies. So it means that no matter which policy you're going to choose, you're going to have the same average number of overlaps there. So there is no escape from overlaps. So the only thing we can do is we can probably arrange them in different ways, but the average number of overlaps is the same, regardless of the scheduling policy. But the other two performance indicators, LBF and ODF, we are going to talk about them here. So for LBF, again, round robin and BIBD are perfect load balancers. They achieve the highest, which is 1, but random, yeah, of course, we know if we throw things randomly into bins, then one bin is going to have more, one bin is going to have less. And that's why, yeah, so the LBF is below 1 and is below the other two policies. And then we have overlap diversity factor. We have ODF, for which random and round robin are achieving the highest. I'm sorry, random and BIBD are achieving the highest, but round robin is inferior in the sense of overlap diversity factor. And it's like when you use round robin, there is not going to be, we are not going to achieve as even overlaps as when we use random or BIBD. But again, this is interesting because random and BIBD, they achieve the same ODF. Basically, they can provide the same evenness across overlaps, and that's something good for BIBD. So basically, the point here is BIBD has the best of two worlds. It achieves the highest load balancing, and at the same time, it provides an even overlap compared to round robin. And that's why we hypothesize that BIBD is going to have a better performance in systems with redundancy. And something else to consider is that when we use BIBD, that create a structure, also imposes restriction on the parameters, where like n has to be equal to d times d minus 1 plus 1. This is specifically for BIBD. Yeah, and if you use any other design, that this relationship is going to change. Another way to look into these overlapping property of scheduling techniques is by looking at their associated graph. So a scheduling policy can be described by a graph, by a bipartite graph, where on the right you have servers, on the left you have jobs, and jobs indexed from 1 to 7 here, but more jobs can have around, like the job 8 can be placed at job 1 and so on. So we are doing a round robin again here. But for round robin itself, we can also see this round robin structure from its graph, and each graph can also be described by an incident matrix, where on the rows you have jobs, on the columns you have servers, and an entry is 1 if a job is assigned to a server. And that's like the round robin. The round robin structure is also obvious from its graph. So once we do that, once we describe a scheduling policy with a matrix, with its incident matrix, then we can measure the spectral gap of the matrix which is basically the difference between the first and second largest eigenvalues. And then it is known that this spectral gap, so the spectral gap, if for a graph this spectral gap is large, it's basically an expander. If it's small, it's not an expander. And so we show that a spectral gap by epsilon, and we can see that so the spectral gap of BIBD is d minus square root of d, but for round robin is d minus sine d pi over n divided by sine p over n. And as n goes to infinity, this spectral gap of round robin shrinks and goes to 0. And so basically the spectral gap of BIBD grows with d and is larger than the one for round robin. And that's also another way into looking at why a BIBD policy has a better overlap structure than the round robin. Do you have any questions up until here? So, all right, so far we have talked about indicators, but indicators that are measured in the analogous problem. But now we want to show some simulation results in actual queuing system where we have, there are n servers, for each job there are d copies. The service time of jobs is hyper exponential, which is described by two parameters. Parameter p, which is the probability of sampling from the faster exponential, and q, which is the relative rate of the two exponential distributions. So a simulation environment is defined by a Ford tuple, which is NDQP. All right, so in our first one, we are looking into a 21 servers with 5 replication, with 5 copies of each job. The Q is equal to 1, which actually makes the hyper exponential an exponential distribution. So in this figure, we are dealing with exponential distribution. And here P doesn't matter because both exponential are the same. All right, so when we do this, we see that, well, random is inferior to both. Round robin has a better, has a less average waiting time in lower loads, and they almost like BIBD and round robin have almost the same, with BIBD being a little better at the end of higher loads. So I think that the question here is why round robin does a better job in lower loads. That's because when load is small, we don't have actually that much overlaps, right? And actually, round robin does a better job for overlaps when the load is small, because in round robin starts with providing no overlap at the beginning. Like the first, let's say we have 21 and 5. The first job is going to 5, the second job to the next 5, the third job to the next 5. So there is no overlap between the first 3. Whereas in the BIBD starts with overlapping things from the very beginning. And that's a way to providing even overlaps. So actually, when the system load is little, round robin does better at that, and because of the reason I explained. But then when Q goes up, Q is the ratio of the ratio of the rate of the two exponentials. When the Q goes high, it means that we have jobs that are small on average and jobs that are larger on average, like 2 exponentials. And then in this case, overlaps are more important, exactly because of the reason I explained at the beginning, where we have mice and elephants, right? And because of that, well, BIBD performs the best, and actually random here does better job than round robin because overlaps are important, and we saw in performance indicators that random has a better overlap diversity factor. And this is what we actually are seeing here as well. And then when we increase Q above that, like Q is 50, then round robin performs much worse. And random and BIBD, they end up having the same performance. And that's because, well, when the difference of job sizes are too much, then load balancing doesn't mean much. We can like blind load balancing, like looking into load balancing by number of jobs, that does not provide any information here. So what we should do instead is just try to diversify the waiting times as much as possible, which is done by either BIBD or random, as they both have the same ODF. I think this is the end of this part. So if you have any questions, I would be happy to answer. Yeah, before going to summary. All right. So yeah,
I'm not sure if it was clear. I mean, this is just a really very specific example. We could have taken mice and elephants to mean, let's say, shifted exponential, where the tail is identical across jobs and the shift is either very small or very big. So that would that's one thing. So there are various ways to interpret, to model a mouse and an elephant, and this is just one specific. And another thing, I'm not sure, Amir, this exiting the queues, whether you mentioned, but anyway, we can discuss that later because you just would like to summarize also the rest of your thesis.
Like one thing I would like to see is the mouse and elephants again, now that you solved the problem.
Oh, okay. Like how?
Like a picture of a BIBD elephant and mice.
Okay, yeah. Yeah, sure. That would be, yeah, you're right. That would be nice to have here.
Thank you.
So yeah, in summary, we studied performance indicators of some non-adaptive scheduling policies. We talked about the role of overlapping servers in the performance, and we developed an analogy to the Urns and balls. We derived the performance indicators for the scheduling policies of interest, and then we proposed this new scheduling policy based on combinatorial designs, and we showed that it outperforms in terms of performance indicators. Then we talked about expansion properties of scheduling policies, and by simulation showed that the block design based policy outperforms. And of course, future directions like driving the closed form for average waiting time of a block design based policy would be something probably very hard, but very interesting at the same time. Designing scheduling policies based on other designs, not only BIBDs, is also interesting, and like trying to lift restrictions imposed to the system by the parameters of BIBDs would be another direction to go.